And we'll see what happens. Anyway, this is another one out of your textbook, although I noticed in looking at my textbook, they've added more problems to all the chapters. So this was problem 31 in one of the textbooks a few editions back, and now I don't know what it's numbered, but anyway. A long thin solenoid has 400 turns per meter and a radius of 1.10 centimeters, and a 6.50 microcoulomb charge moves in a circular path centered on the center of the solenoid. So, and the circular path is 3.50 centimeters in radius, so it's bigger than the radius of the solenoid, which means it's outside of it, and lies in a plane perpendicular to the axis of the solenoid. And if the charge moves around the circular path in the direction of the induced electric field, how much work is done on it during one complete trip around the path? So let's kind of make a sketch for this thing. And we'll look down the axis of the solenoid here, and it has a radius of 1.10 centimeters. And let's see, in the direction of the induced electric field. So there must be a changing magnetic field within this region. So the current in the solenoid must be changing in some way, but then we've got a circular path that goes around the outside of the solenoid, and first it's got a radius of 3.50 centimeters. So, and this is not a scale diagram. Then we have a charge that's actually moving around this circular path for some reason. Now, when you have a changing magnetic flux in some area, there will be electric fields that are generated. And when you have the cylindrical symmetry like you do here, the induced electric field will be a circular loop. And so we can go with that there. Let's see. In a plane perpendicular to the axis, okay. I wonder if I forgot to copy down some crucial information from this. Because, yeah, I better check this problem if I can find it in your textbook. Seems like we're missing some information. Was problem 31. Not those things. Oh, yes, I think. Well, maybe not. Long, thin solenoid. There it is. Oh, okay. I missed a sentence. The current in the solenoid is increasing at a uniform rate, di dt. So that's equal to a constant, and the current in the solenoid is increasing at that rate. Okay, otherwise, if it was a constant magnetic field, there would be no induced electric field. So you had to have that. Now, since it is a solenoid, the magnetic field is going to be mu naught N times I. So we'll have that. What else do we have? Oh, that's mu naught. Let's see, 400 turns per meter. So that's the N. We'll have mu naught. So that'll be the magnetic field within that solenoid, and we can calculate the flux because the magnetic field will be perpendicular to this area. So the actual flux that's inside the solenoid, the magnetic field of a solenoid is zero outside of it. So that's something to keep track of. And you might have to read back to the previous chapter, but it'll equal B times the area of the solenoid, which is just going to be B times pi r squared, which in this case will have mu naught n, and they're using a lowercase I for the current, so we can do that, I guess, in I times pi r squared. And the thing we're interested in is the time rate of change of the flux of the magnetic field, and d phi sub b dt. Still think I may be missing something on here, like a value for di dt. Long thin solenoid has 400 turns. I think I may have copied part of one problem and part of another, and I don't think this one has enough information. So let's can this one, do something else. Okay, yeah, this one we can do. It's complete. I don't know what in the world is going on with that problem, so definitely have to check that one and find out where in the world I got it from. Anyway, this time we've got another long thin solenoid, 400 turns per meter and a radius of 1.10 centimeters. Yeah, I think I started typing in this problem and somehow got going on another one. The current in the solenoid increasing at a uniform rate, di dt, and the induced electric field at a point near the center of the solenoid and 3.50 centimeters from its axis is 8.00 times 10 to the minus 6 volts per meter. Okay, so we kind of have the same geometry here that I sketched over here. So this was correct at least. And then it looks like I finished copying another one. And this is something where I was looking in the book and typing it. So I'm amazed I never found that before. Okay, but this time we're out there 3.50 centimeters out, and we can use these relations that we've got, like for instance, if I do this E dot dl around a closed path, that will end up equaling the flux of B dt. So it'll be the time rate of change of the flux. Actually, we put a minus sign on here, but we're just interested in the magnitude of the rate at which the current is changing. But for a solenoid, part of what I wrote down with that wrong problem was correct, and that is that the flux of the magnetic field will equal the magnetic field strength times the cross-sectional area of the solenoid. And again, we won't have, and this is kind of weird. The magnetic field is confined to this area, and the flux of the magnetic field is confined in here, but it's producing an induced electric field that is out here, which is just mysterious as all get out. But we'll have B times pi r squared. B is mu naught n, and here we're using a capital I, mu naught n I times pi r squared. So we have that. We're mostly, and R is the radius of the solenoid. And d phi sub b dt is going to equal, well, the only thing that's changing in here is the current. And so it'll be mu naught times n times pi r squared times di dt. And we're after this quantity. Now, this will equal an integral of E dot dl around any circle we happen to choose here. So this is kind of interesting. But if we make a circle of radius 3.50 centimeters, we find out that the strength of the electric field is 8 times 10 to the minus 6 volts per meter. Well, the induced electric field will form concentric rings around this current. And so if I do an integral in this direction, an E dot dl around there, the electric field will be constant and it'll always point in the direction of dl. And so this is something that by doing a bunch of these problems, you kind of get comfortable with this idea. You choose integral paths that are advantageous. E and dl are always in the same direction. So I'll have this integral E dl, and E is a constant, so it can come outside there. We stay the same radius away from the center of the solenoid. And I'll just have E times the integral, still around a circle, of dl, and that'll be E times, I'm going to call this R2, times 2 pi R2. And R2 is going to be the 3.50 centimeters. So okay, but this is going to equal that. And so E times 2 pi R2 is going to equal mu naught n pi, I should call that one R1, I guess, R1 squared times di dt. And it said that induced electric field has a strength of 8 times 10 to the minus 6. So I know this. I know my R2. I know R1. And the only thing I don't know is di dt. So let's see what happens here. Solving for di dt, I will get E times 2 times pi times R1 divided by mu naught pi R1 squared, and those pi's go away. So let's just stick in the numbers here. E is 8 times 10 to the minus 6 volts per meter. And the units might be fun on this. 2 times R1 was 1.10 times 10 to the minus 2 meters. Whoops, that was supposed to be R2 up there, which is 3.50 times 10 to the minus 2 meters. And then on the bottom down here, I've got mu naught, which is 4 pi times 10 to the minus 7th. Nah. Then my usual struggle with the units on this, although last night I figured out something. It's a magnetic constant, Webers per amp meter, but a Weber is a unit of flux. It's Tesla meters squared. So I think I can handle that. Tesla meters squared per amp meter, which looks like Tesla meters per amp, I think. Okay, and then R1 is the 1.10 centimeters. So 1.10 times 10 to the minus 2 meters squared. Whoosh. All kinds of stuff on here. Okay, I need to check the units on this to convince myself that we're not on the wrong track. Okay, a volt per meter times a meter is a volt, which is a joule per coulomb. And that's what I have on top of that fraction. On the bottom, I'll have Tesla meters per amp, Tesla meters per amp, times meters squared. But a Tesla is a Newton per amp meter. So a Tesla meter per amp. Oh, I'm going to have, let's see, what am I going to have? Whoops, the amps don't divide out. I'll have amps squared on the bottom, newtons per amp squared times newtons per amp squared. I hope. Let's see. Okay, and now I'm starting to wonder, the IDT should be amps per second, I think. And that's not what I'm seeing. I would have, maybe I am Newton meters per amp squared times another meter. And this is the joule. So that takes care of that joule, and this will be 1 over coulombs. So 1 over coulombs times a meter over an amp squared. Is an amp squared over a coulomb meter. Yeah, I screwed up the units here somewhere. Rats. Well, that was correct. Volts per meter. Oh, this would have been better to think of as coulombs per, or newtons per coulomb. Let's do that. Newtons per coulomb times a meter. Oh, shoot. Sorry about this. My mind is elsewhere today. I should have gotten more sleep last night. Yeah, I'm just going to start over with these units and try to figure them out. And I'm going to go back to my other version of mu naught that I like better. Then I need to fix those units in there. Tesla meters per amp. And I've got to fix this. Okay, there we go. Tesla meters per amp. And maybe I screwed up, if that's possible. So I'll have volts per meter, or E is also newtons per coulomb. I'm going to go with that. Newtons per coulomb times a meter on top. And then mu naught, which I just wrote down, is Tesla meters per amp. Yeah, that's right. Times meters squared. Yeah, Tesla meters per amp. And a Tesla is a Newton per amp meter times a meter per amp times a meter squared. And this is all on the bottom. I think maybe I can do something with this. So now I've got a new bottom. Newton meters over a coulomb divided by a Newton per amp squared times a meter squared. Newton meter squared. The newtons will go away. Huh. Yeah, maybe I'm ending up with the same thing again. Newton meters per coulomb times an amp squared per Newton meter squared. Those go away. You guys see a way out of this fix. So amp squared per coulomb meter. Oh, somehow I lost my N, which was 1/meters. Okay, so I should have my N in here, which is 400 meters to the -1. That was something I lost. Okay, and actually, times 1/meters. So those are gone, and I've got amp squared per coulomb. And an amp squared is a coulomb squared per second squared. I'm getting too many seconds here, divided by a coulomb. So I'd have coulombs per second squared. And I don't know where that other second went. The IDT. Yeah, I'm baffled. But at any rate, I'll figure out this thing. Anyway, that's the way that you could calculate the IDT, except I think I lost something else somehow because I've got an extra second on the bottom of my expression. So sorry about that. Let's do another problem. When in doubt, move on and come back to that one later. In the figure below, the loop is being pulled to the right at a constant speed V. A constant current I flows in the long wire in the direction shown. So current is going up. With current going up, use your right-hand rule, point your thumb in the direction of the current, and the magnetic field over here is going to be into the page, but it is not constant because it gets weaker as you move away from the wire. The magnetic field of a long straight wire, B, is mu naught I over 2 pi r. So it'll be getting weaker as we go over in that direction. Calculate the net EMF induced in the loop. Okay, well, I don't necessarily have room to do that here, but I can do this. I can calculate, take a thin sliver of width dr here, and the magnetic field, if that's a distance, oh, now I'm supposed to use a little r. Oh, it's being pulled to the right, so r is something that's changing. I'm going to call this, well, I'll let this thing, let r be the instantaneous distance of this side away from that, and I'm going to let x, now this is a letter x, not something representing the magnetic field into the page, x be that, and this will have a width of dx, and the magnetic field inside this little sliver is going to be mu naught I over 2 pi x, And let's see, the flux through this thing is going to be B times dx times B. So this will be a little bit of flux, d phi sub B, and it will be mu naught I over 2 pi x, that's the magnetic field strength, times the area of this little sliver, which is going to be little b dx. So lowercase b dx. And let's see. Oh, I have to integrate this thing to figure out the total magnetic flux through that square loop. So the flux of B will end up equaling, well, everything's a constant here. It'll be the integral going from x equals r to x equals r plus a. So from r to r plus a of all this stuff, mu naught I over 2 pi x times little b dx, and I'll pull out all the constants, and what's left inside is just going to be dx over x. So the flux of B will equal mu naught I times B over 2 pi, and then I've got this integral of dx over x from r to r plus a. Let's see, r to r plus a. And that turns into the natural log of the ratio of those two things. So mu naught IB over 2 pi times natural log of r plus a divided by r. And, oh, we're supposed to, let's see, calculate the net EMF induced in the loop using Faraday's law of induction, which is the d phi sub b dt thing. And then also by looking at the EMF induced in each segment of the loop due to its motion. Oh, so we're needing to consider motional EMF here, which I kind of introduced the other day, but not very well. So we'll have to see this. I'll have to reintroduce that. And what did I do with my notes on that? I'm going to need more room to finish this anyway. If I just consider this square area and imagine integrating it, the induced EMF is going to be the time rate of change of this thing. Now, that won't give me the electric field at any given point. It'll just give me the I'll be doing this. The induced EMF is going to equal the integral of, I'm going to bypass this middle part actually. Actually, it's the negative of the integral of E dot dl, but that'll equal d phi sub b dt in that area. And I just imagine integrating around that area, but that'll give me this. So I'm bypassing the middle part. I'm just going to say the induced EMF is going to be d phi sub b dt. And I can take a time derivative of this thing. And the only thing that's changing in this expression is r. And so I'll have mu naught IB over 2 pi, and then d by dt of that natural log of r plus a divided by r. And so seems to me the derivative of a natural log is 1 over that thing, 1 over whatever's inside. But in order to do this, I'm going to split this back apart. I'm going to think of this as d by dt of natural log of r plus a plus the natural log of r. And so take a look at that. And that ends up being, let's see, 1 over r plus a times dr dt. Whoops, this was supposed to be a minus 1 over r times dr dt. That's the chain rule in action, I think. And I don't know where, there's my, I don't know if I have derivatives in this or not. No, I don't. I'm going by my memory, assuming that's what the derivative of a log happens to be, because the integral is the antiderivative. Derivatives. Yeah. I think I'm right. And I know what dr dt is. It's v. So this all ends up being, everything's more complicated today. 1 over r plus a minus 1 over r times v is what all of this time derivative stuff is. But I can maybe simplify this, get a common denominator. I'd have r minus r plus a over r times r plus a times v. I don't know if there's any point in doing that. I end up getting minus a over r times r plus a times v. I don't know that that was that helpful, but maybe it was. Okay, but I'd end up with an induced EMF of mu naught IB over 2 pi. B, think I've got everything there. And then times this thing, or that. Maybe I'll stick with that one. It looks simpler. 1 over r plus a minus 1 over r times v. So the induced EMF is proportional to the speed at which you're pulling this thing away. All right. So that was part A. Calculate the net EMF. Do that 2 ways, using Faraday's law of induction and by looking at the EMF induced in each segment of the loop due to its motion. Okay, for that, I need to introduce that motional EMF, which is, telling you my page isn't going to help much, because I've probably got a different edition of the book than you do. Okay. This would be the part A thing. So that's using Faraday's law of induction. Part 2 is to look at the EMF induced in each segment of the loop due to its motion. And here's induced EMF as a result of motion. And this is introduced in the chapter section on motional electromotive force. And when you have the length and velocity perpendicular to the uniform magnetic field B, as we do only for this part and this part, turns out for something that is parallel to the velocity, there is no motional EMF in this part of it. So we're just going to have this. And what that's going to equal is the induced EMF in part of it. Let's see, B cross B. Going to be in that direction. Oh, the current. Actually, they're both going to be the same, but they'll be battling each other. I will have equal to, and I'm going to call this E star equals V B L. And the length in this case is lowercase b. The v is just what they gave us, it's v. But the b for the left part, and this is the left part of this rectangle there, is going to equal, E will be V times mu naught I over 2 times pi times lowercase r. And then the length of this is B. So does that look like anything we've got? Kind of. Like that. And then for the right part, we'll have, I'll call this E sub L and E sub R. We'll have V times mu naught I over 2 times pi times R plus A times V. I think this is going to work. Oh, no, we already had a V times B. That's what goes over here. Okay, and these are actually opposing EMFs. They're both going to be in the same direction. They'll both be up in this direction. And so the net EMF for the loop is going to be the difference between these two. And if we take the bigger one, the one on the left, minus the one on the right, let's see, or actually I should have had the negative of that. Faraday's law would have a minus sign on there. But anyway, the EL minus ER, which is the net EMF, because if we're going opposite in EMF, we put a minus sign on it for our little loop there. Sorry about all this. But anyway, we'd have mu naught IB over 2 times pi times yeah, 1 over R time, actually mu naught IB, I've already got the B times V. I don't want to lose it. I'm moving it from there. Minus mu naught IB over 2 pi times 1 over R plus A times V. And actually, we end up with the same expression. I've just got it opposite on there because I should have had a minus sign on here. The induced EMF is minus. And so if I put a minus sign in front of this, I'd swap the order of those. So another complicated problem. Find the direction clockwise or counterclockwise of the current induced in the loop. Well, as you pull it this way, the magnetic flux through the loop is going to diminish, and it diminishes because the magnetic field is getting weaker, and so the induced EMF will be in a direction to oppose that diminishment of magnetic flux through here, which will happen if you have an induced EMF that's clockwise, making a current flow clockwise, which will make a magnetic field into the page, which will oppose the diminishment of the flux through the loop. So that's something that we can get by Lenz's law. But if we think about the magnetic force on the charges in the loop, V cross B is going to be the magnetic force on the charges. It'll be upward in both parts, but it's stronger in this part because the magnetic field is stronger on that end of the loop. And so the magnetic force on the charges in this part of the loop is greater than the magnetic force here. That's an EMF. And so the current would tend to be clockwise for that reason as well. Okay, and then check our answers in special cases to see if it's reasonable. One, if the loop is stationary. Well, if the loop is stationary, it's just sitting there in a stationary magnetic field. V is 0, and so there's no induced EMF, and both of our expressions would go to 0. So that's reasonable. And then if the loop is very thin, so A goes to 0, and the loop gets, so if A goes to 0, if I look at this, if A is 0, I've got 1 over R minus 1 over R. There's no flux through a loop of width 0, so it makes sense that it would vanish in that case. And then the final thing is the loop gets very far from the wire. Okay, well, if the loop gets very far from the wire, then R is much greater than A, and this is going to be, this will be essentially 1 over R, and this will still be just 1 over R. And so these terms get much closer to each other, and the difference between them actually goes towards 0 as you get very far from the wire. So there's no induced EMF. And as you get very far from the wire, the magnetic field is so weak that it's just not going to induce much of a current. And so all of those things make sense with the expression that we have there. Let's see if I can. Perhaps. Here's one that we can actually try out. A powerful electromagnet has a field of 1.60 Tesla and a cross-sectional area of 0.200 meters squared. Okay, from that, knowing that cross-sectional area and this thing, we can figure out the magnetic flux through this thing. And if a coil of 200 turns with a total resistance of 20 ohms is placed around the electromagnet, and then the power to the electromagnet is turned off in 0.0200 seconds, what's the induced current in the coil? Okay, well, this would be an induced EMF, which is going to equal the time rate of change, and usually it's a minus d phi sub b dt, which in this case is going to be minus d by dt of let's see. Yeah, just b times a. Oh, except I have to multiply this by n because I've got n turns in my coil, wherever it happens to be. So it's just being wrapped around this electromagnet. So NBA, and that will equal, E is equal to the induced current times the resistance of the circuit. And the greater the resistance of the circuit, the less the resistance is going to be, because this part's going to be fixed. Except in this case, instead of calling it a d by dt, we can think about a delta phi sub b over a delta t. It's a pretty short time interval that we're shutting this off in. And so we can kind of treat that like a derivative. And so we'll have n times that is going to equal the current times the resistance in this case. This is Ohm's law, E equals I times R. So it's not around a particular or for a particular electronic component, it's for a complete loop of wire that we have, or a coil of wire that we have wrapped around it. But it still works. So, okay, so we take the delta phi sub b over delta t. So that's going to equal, originally, b times a initial will equal 1.60 Tesla times 0.200 meters squared. And this is a Tesla meter squared. That's what a Weber is. A Weber is actually a unit of magnetic flux, which I'd forgotten until last night. I happened to look it up again. But anyway, 1.60 times 0.2, I think, comes out to 0.3220 Tesla meters squared. BA final, the power to the electromagnet is turned off. So BA final is equal to 0. And delta phi sub b over delta t, I'll divide this by 0.0200, and we'll see what happens with that. But then I've got this N over here, my 200 turns. Boy, there's twos all over the place in this case. And a turn is dimensionless. It's just a pure number. And so we'll have delta phi sub b, which is 0 minus 0.320 Tesla meters squared, divided by the delta t, 0.0200 seconds. And that will equal I times R. Okay, looks to me like we've got Tesla meters squared per second here. And somehow that's supposed to equal volts, which I bet it does. It'd be handy to write down the solution to every one of these problems and just see how that happens to be. But let's work it out again. A Tesla is a Newton per amp meter times a meter squared, and I'm dividing by a second. Oh, the joule per amp. Times a Oh, yeah, Newton meter is a joule. Oh, actually, I'd have amp second, which is a coulomb. Yes, it's a joule per coulomb. It's a volt. So whatever number we get here, it's a volt, and I'll be dividing by a resistance, an ohm, and a volt per ohm is an amp. So hooray for that. And I know these are all easy things, but I'm not trusting myself today. Um, okay, I actually get minus 3,200 volts on this side, and then I'm going to have I times whatever the resistance, 20.0 ohms. And we should have been able to figure this out, but in our heads, math-wise, I get a lot of amps here. Um, equals 1.60 times 10 squared amps. That'll fry your basic or vaporize your basic wire if it's not too thick. That's a lot of amperage. And but this is a strong magnetic field and it's turned off in 2/100ths of a second. And so that would induce a large current in a wire. And so that's something you'd have to be cautious of. Okay. Does this one look reasonable? Um, this one's, yeah, this will be the last one we do, I think. This ought to be enough. We have a long straight wire carrying a current that varies with time as I equals I naught sine of omega t plus delta. Okay, now omega is just going to be a number. Delta is not going to matter. It's going to vanish when we take a derivative of this thing. And anyway, this is the way alternating current varies. It varies sinusoidally with time. At least if it's pure alternating current, you can get um, stuff that's not so pure, but that's what it usually looks like. And it lies in the plane of a rectangular loop of n turns of wire as shown in the sketch. The quantities I naught, omega, and delta are constants. Determine the EMF induced in the loop by the magnetic field due to the current in the straight wire. And so it looks to me like we're going to have to integrate again. So we'll imagine. Now, I think we've done this at timer 10 now, not 10, but about 3 of these problems, but it doesn't hurt to see it once more. I'm going to let X point to the right and pick a little slice of this thing that'll have a width dx. I think this is supposed to be a lowercase l. I don't know what happened when I made my drawing, but omega n. This was supposed to be L, I think, equals 20 centimeters. Anyway, the little dA here is going to equal L dx. Okay, the height of this thing times its width. And we can figure out the little bit of flux that's through that thing. D phi sub B is going to equal the strength of the magnetic field. Current's going up, so the magnetic field will be into the page here. And so it'll have, I'll just call it B of X, the magnetic field as a function of X, times dA. And dA is L dx. The magnetic field as a function of X is going to equal B of X will equal mu naught times I divided by 2 times pi times X. And X is going to be the distance that we are away from the wire here. So that's it. And then, so the d phi sub b will end up equaling, let's see, mu naught I over 2 pi x times dA, but dA was L dx. And we can put numbers on all of these things. Now, the net magnetic flux through that coil, phi sub b, is going to equal the integral. The variable here is x, as x goes from a to a plus b of this expression, mu naught I over 2 pi x times L times dx. And mu naught I, L, and 2 pi are constants. They can come out. And I'll have the integral of dx over x evaluated at these two things. I just did one of those. Mu naught I, L over 2 pi. And I'll flip this piece of paper around so I can write on another corner of it. Yeah, we can still see that stuff. And then what I'll have is the natural log of x evaluated at a and a plus b, which ends up equaling the flux of b is going to equal mu naught I L over 2 pi times the natural log of a plus b over a. Okay, so there's our flux of b. And we're supposed to determine the induced EMF in the loop by the magnetic field due to the current in the straight wire. Okay, well, if I is got this sinusoidal variation on time, it's the only thing that's going to change in time in this expression. So the induced EMF is going to be the time derivative of this thing, but everything's a constant except I, and so I'm going to move them to the front of my expression. D phi sub b dt, and this could, we can stick a minus sign on there. It'll be minus mu naught L natural log of a plus b over a divided by 2 pi, and then di dt. But di dt is going to be the derivative of that thing. Okay, well, take a derivative of that. The I naught's constant, and I'd have d by dt of the sine of omega t plus delta, and that will equal di dt. I naught derivative of the sine is the cosine, so I would have a cosine of omega t plus delta. And then the derivative of the inside, delta is a constant, so I'd have d by dt of omega t plus delta. I think that may be the chain rule I'm using. I can't remember. It's been a long time since I took or taught calculus, actually more than 20 years since I taught it once, but I didn't teach the first quarter derivatives. So anyway, the derivative of the inside is just omega, is all you get when you take a derivative of omega t plus t with respect to time. So times omega. So I naught omega cosine of omega t. So our induced EMF is going to look like minus mu naught L natural log of a plus b over a divided by 2 pi times di dt. That was supposed to be di dt, which is I naught omega cosine of omega t plus delta. And So I don't have to figure it out at any particular time. I can just plug in numbers for all these things. So, but we can at least evaluate all of this stuff. We don't know a particular time, but this will all multiply out to give us a constant, which had better be in amperes. So I'm going to flip this one around and do it over on the right side of this. So let's evaluate this. Mu naught I or mu naught L natural log of A plus B over that. So mu naught minus mu naught 4 pi times 10 to the minus 7th. Yeah. Tesla meters per amp. My favorite units for it. Tesla meters per amp. Somehow we're supposed to end up with amps. L was 0.200 meters. Natural log of A plus B, let's see. A and B equals 5 centimeters, so A plus B is 10, and 10 divided by 5 is 2.00 to 3 sig figs. Natural log of 2.00. I naught is 50.0 amps. And omega is, let's see, 2.00 times 10 squared pi seconds to the minus 1. Oh, yuck. Pi seconds to the minus 1, or per seconds. Oh, and I forgot. I need to have an N on this blasted thing. So there should have been a 100 on all of this stuff. So I'll just put that N times N. So we'll have 100 out front here. And sign. Okay, so that's the numerator, and the bottom is just 2 pi. So this 2 pi, or this pi, can divide out that pi. Yeah, I don't know what else we can do. We can just multiply that out. But let's see if it comes out right unit-wise. I'll have Tesla meters per amp. I'll have meters there, and I'll have more amps. And I'll have seconds to the minus 1, which puts them down there. A Tesla is a Newton per amp meter. Newton per amp meter. Well, so far I've got my amps on the bottom, which isn't necessarily where I wanted them. Let's see. That would give me a Coulomb. Oh, no, I'm after an induced EMF. I'm thinking back to the last problem. So I actually want joules per Coulomb, and this is going to work. I'll have Newton meters, which are joules. I'll have amp seconds, which are coulombs, because an amp is a coulomb per second. So I have newtons per coulomb, or joules per coulomb, which are volts. Yay! So whatever that all multiplies out to, and I just don't feel like doing it. But anyway, it would come out volts, which is good. So we'd have a, because of that current that's varying sinusoidally over here, I would have an induced EMF in this thing, which is also varying sinusoidally. It's still got this thing tagged on to the end of it. And so you'd get a an AC voltage in that thing as well. So that's how that works. Okay, sorry about the disorganization at the start with me losing track of units on one, maybe. And I'll have to go back and look at that one, but also having that problem that was not correctly copied. So I'll try to fix that. Tomorrow, we are going to be starting special relativity. And I'm going to start it, as I said, with a brief history of Einstein. And then we'll introduce the very first idea of special relativity that we'll look at. And it's called time dilation. And it has to do with the way time is perceived differently in different reference frames. So kind of mind-boggling, and at least one of the problems we'll do, if not tomorrow, we'd be doing it on Monday. But one of the problems, we're going to introduce something that we have to do for some of these relativistic problems, and we actually do a series expansion. And that's something that we haven't done before, I don't think, but it's going to be something based on the binomial theorem. And so by the end of the relativity unit, hopefully you'll be able to do that on your own. So that's something that we'll do tomorrow, and I'll stop the recording.